Hey guys, what's going on? Welcome to your first lecture for electrical class. Now, this is very similar to the one that you took, or the lecture that we had and the worksheet we filled out in intro. Why is it very similar? Well, I feel like it's a good way to kind of ease into the course. I think there's a lot of value in hearing things multiple times. The lecture that I gave you guys in intro, is kind of boiled down like the whole course is kind of like, here's like a very good introduction, I guess for intro course, right? So why not rehash that and kind of talk about those important things before we get into the nitty gritty, okay? Because what are we really talking about? The fundamentals of electrical, okay? So this is for worksheet number 1, electrical fundamentals, hall number chapter 39, okay? So we're going to talk about the fundamentals of electricity. And really, what is electricity? Really, it's the movement of electrons through a conductor, okay? Talk about the units of electrical measurement. Talk about the relationship between volts, amps, and ohms, okay? Electrical pressure, current flow, and resistance. We're going to go into this much more in detail when we talk about Ohm's law. And it's that relationship is, I believe, the key to solving electrical issues, okay? You got a light bulb that's dim. Why is it dim? Right? Something isn't giving it the power that it needs, right? Well, what's power? What is watts? Why you have a 60-watt light bulb? What is watts? Okay. Well, watts, the power, the output of the light bulb is voltage times current flow. So volt times amps is how you determine watts. Okay. If you have a corroded connector or a bad ground, that is high resistance, right? That is like stomping on the hose. Stopping on a water hose, right, on a garden hose, you're going to lose flow, okay? You lose flow, the pressure may still be the same, but you lose flow, you lose wattage, right? So your bulb is dim, okay? So like that relationship is going to be key, absolutely key. Just breaking it down that simple. Why don't I have ground? Well, high resistance, right? Anyway, so I mean, obviously, we're going to be taking this entire course, and then we're going to take a second electrical course where you put the stuff into practice. So bit by bit, right? You hear it many, many, many times, and that's how it builds up in your head, okay? Talk about the different sources of electricity, and talk about conductors and resistance, okay? Or even conductors and insulators, right? Okay, so why does everyone have trouble with electrical? Okay, well, for one thing, it can't be seen, okay? Only like the results of electricity can be seen. You got a clunk in your front end, you put it up in the air, you shake the wheel, you're like, oh, I got a loose tie rod, I got a loose ball joint, the control arm bushing is rotted, okay? You can see that, right? Why do I have grinding in my brakes? Pads are metal, all right? Now, just like we were talking about with, a dim bulb, right? If a bulb's out or something, yeah, maybe the bulb is bad. Maybe it's not. Maybe it's a corroded connector or a terminal or a wire. Okay. It has to be detected and measured, and the results need to be interpreted. All right. So you have a dim bulb and you look and you only have 9 volts there. Why do you have 9 volts? Okay. You have to interpret that and realize that something is stopping that voltage from getting there. Okay. Okay, so just electrical systems, a brief history. All right, early vehicles didn't have electrical systems. All right, the first electrical components in cars were batteries and powered lights and stuff like that. Right, you didn't really have an alternator or a generator constantly generating voltage for the accessories and everything. After 1912, the self starter and battery became commonplace. Batteries were really kind of SLI batteries, right? Starting, lighting, ignition. Just the main important stuff, I guess, right? The points type ignition system. I'm not going to get too much into ignition systems until we talk about electromagnetism, and then further when we talk about ignition systems in the energy performance classes. But I want you to just think about this for a second. You have a battery that's 12 volts. Okay. 12 volts isn't a lot, right? You ever stick a 9-volt battery on your tongue? 12 volts isn't really that much more, okay? I wouldn't do that with a car battery because, it's a little more juice behind it, but it's not a lot of juice. Now, how do you fire a spark plug? Do you know how much spark plugs have? 20-ish thousand volts, maybe a little more, depending on the system. So how do you get 12 volts and you make 20,000 volts out of it? Okay. Electromagnetism, some really, really cool stuff. I think it's one of my favorite units to teach because when I first relearned it to teach it, I'm like, oh my God, dude, that's some crazy stuff right there. All right. 1920s and 1950s, radios were coming in cars, defroster fans, horns. And then, it kind of had the plush side of things, power seats, air conditioning, power windows, and then the electrical demands got more and more and more and more. And I mean, think about it nowadays, how many memory seat systems do you have? How many, I can't even, begin to fathom, they've come a long, long ways, right? And the electrical systems and the battery technology really hasn't advanced that far. It definitely hasn't advanced as far as like the demands that it needs, right? So that's kind of a challenge in automotive, right? I mean, obviously, hybrids and stuff like that, but like the battery technology itself hasn't really come a whole long way, right? Okay, common electrical components: climate control, power windows, security system, electronic power steering. Now you don't really see a whole lot of hydraulic power steering anymore. Electronic suspension. Okay, MagneRide, stuff like that. Heated seats, infotainment, Bluetooth, videos, all that good stuff. So let's boil it down here. What exactly is electricity? Okay. It's the movement of electrons, right? It's electrons flowing. That's why you have current flow, right? When you have water current, the water is flowing. When you have electric current, the electrons are flowing, okay? The movement of electrons from one atom to another, okay, at the molecular, atomic level, even smaller than molecules, right? Okay, so an atom, we got to know the parts of an atom first, okay? You have a nucleus, the center, which is positively charged because you have a neutron and a proton inside of that, okay? And then you have an electron, which is negative, in the rings outside there. It looks a lot like a solar system, right? Oh, look at that. Solar system. Crazy. All right, so define the parts. The proton, okay, this is located in the nucleus. It is positively charged. You also have a neutron, also in the nucleus. It is electrically neutral, hence the name. There is no charge to that, okay? Now, electrons, they orbit the nucleus, okay? They're negatively charged. Okay, so electrons are really going to be, well, you have a positively charged nucleus, and you have the electrons in orbit, okay? If an atom has 5 protons, generally a stable atom, has the same number. You got 5 protons in there, you got 5 electrons going around the outside, okay? It's the number of electrons that determines the material and how how electricity is conducted. Okay, overall, an atom has a neutral charge. Do you guys know what it's called when it doesn't have a neutral charge? An ion. Okay, that's going to be important here in a second. All right, not Saturn ion, but atomic level. Okay, so overall, an atom, a stable atom, has a neutral charge overall. Okay. Here's a balanced atom. You got what? 6 protons in the nucleus, and you have 6 orbiting electrons, okay? Now, that doesn't have any electrical potential, does it? All right. Now, what happens when you charge a battery? We'll talk about that in a little bit, too, okay? Well, first of all, let's talk about magnets, okay? The 2 ends of the magnets are called poles. You have a north and a south, okay? Unlike charges, they attract each other. Take a north pole and a south pole, and they're going to boop like that. Like charges, you got the north and you got the north, and they're going to repel each other, right? It's going to kind of, it's like little train toys. You put them against each other, and one way they hook up, and then they go, and the other way you switch it around, and then they kind of like push against each other. There you go. Unlike charges attract, like charges repel. Hopefully we all know that by now. Let's get into ions here. Okay, an ion has an imbalance of electrons or protons. It can either be negatively or positively charged. Okay, just like with heat. Okay, it wants to be equal. Okay, so if you take a cold, if you take an ice cube and put it on your hand, right, the heat, your hand gets cold and the ice cube gets warm, right? So it wants to even out, right? Electrons will flow to even that out. So if you have an imbalance of electrons, you got a lot of positive over here, you got a lot of electron or negative over here, a lot of electrons, they're going to kind of go over to this side and it's going to even out. Okay, like a battery. When you charge a battery, and when we get into talking about batteries and how they work, you'll see that, you know, through the plates and the electrolyte, they have an imbalance in there. That's a charged battery with 12.6 volts. And then as it discharges, all of a sudden, those electrons all flow and it evens out, and then you have no charge left, right? The battery is dead. All right, so, okay, an unbalanced positively charged atom, which is an ion, will attract electrons from neighboring atoms, okay? Now, electrons, just like orbits, okay, of the planets. Earth has its own orbit, so on and so forth, right? These are the electron shells. There can only be so many electrons in each shell, okay? They're the orbits around there, okay? Once one orbit gets filled up, the next one, they start to go on to the next one. Then they go on to the next one, they go on to the next one if you have, you know, however many electrons it has, okay? Hydrogen atom, you have it with one electron, okay? You got one proton, one electron. Aluminum atom, you got 13 electrons, and I want you to look at this outer ring right here, okay? Because this is gonna come very important. You only have 3 on here. Copper atom, you only got 1 on that outermost ring. Silver atom, you also only have 1 on that outer ring. You got 61 total, but you have 1 on that outer ring. Now that outer ring is called the valence ring, okay? And we're gonna get to that in a few slides here. It's the number of electrons that you have floating on that valence ring, which determines, look at what we got here, aluminum, copper, and silver. Are those electrically conductive, or would they be an insulator? Okay. The outermost electron shell ring is called the valence ring. Okay, and this, like I was saying, is most important. It's the number of electrons in the valence ring that indicates the capacity to combine with other atoms. Okay, to conduct, to move electrons. Okay, if you have a solid full valence ring, they're not going to move that easily, right? An insulator, rubber. If you have 1 or 2 or 3 just floating around on that valence ring, they're probably going to be picked off pretty easily, right? Conductor. Okay, so here you go. Look at this one. Orbit levels. See, these are all bound electrons. It's all full. And then you got that free electron right there, okay? The free electrons drawn away from the atom. Other free electrons, right? There's not a whole lot keeping it there. So, conductor, an atom with fewer than 4 electrons in its valence ring, okay? They're loosely held, they can drift easily. That's why they're conductors, right? They can flow electrons super easily, okay? There you go, conductor. That one's only got 1. 3 examples of conductors: copper, gold, steel. Now, gold. Those of you guys that are big into like audio systems or know that airbags, they're connectors, they're terminals, right? They're coated in gold. Why are they coated in gold? Is it the best conductor? No, it's not. It's because gold does not corrode. Okay, copper corrodes, steel obviously corrodes, aluminum corrodes, right? But gold doesn't corrode. So if you want a good connection that's not going to corrode, gold's your way to go. If you go out to your yard and you dig up like gold, I don't know, maybe, you know, in the gold rush or whatever, you're like, oh man, look, it's gold. Not like, oh, here's a piece of rust, right? It's gold. It doesn't corrode. Copper. Why do you think we have copper wires? Right now, copper does corrode, which is why electrical diagnosis is very good, or very important to understand that, because being an automotive technician up north, you're going to see a lot of corroded wires, corroded grounds, all that type of stuff. Okay, this is all the salt in the road. So that's gold right here. Not as good as copper. Obviously it's really good and everything, but it's because of the corrosion. Boom, look at that. Airbag connectors. Gold can be buried for hundreds of years, and when dug up, it is just as shiny as ever. Look at that. I almost knew the slide was coming. I should have waited for it. Water, okay? Here's another thing. Pure water is an insulator, okay? But there's a lot of crap in water, right? So that's what actually conducts, is like the stuff inside of it, all right? So insulator. It is a material with more than 4 electrons, okay? So you have less than 4 and you have more than 4. What is 4? We're going to get to that later, okay? An insulator, a material with more than 4 electrons in its valence rings. Obviously, if it has more than 4, it's going to be tightly held. The electrons aren't going to flow easily. You're not going to have the conducting of electricity. It's an insulator, okay? There you go. Look, this one has 6. 3 examples: rubber, porcelain, ceramic, okay? This is why you see porcelain, ceramic, rubber being used as insulators, right? Now, a semiconductor, okay? A material with exactly 4 electrons in its valence ring is a semiconductor. Semiconductors have exactly 4, and, sorry, I'm trying to actually use the slides here. Silicon, okay? Germanium, carbon, okay? These are all stuff used in electronics, okay? Because they can be doped to conduct electricity very easily. And that's going to a whole nother thing. We'll talk about that later when we talk about transistors and stuff, okay? All right, so what causes electrical current to flow, okay? It's an imbalance of electrons. There has to be an imbalance of electrons, because electrons have to be moved somehow. A positive charge has a lack of electrons on one end. A negative charge has excess electrons on the other, okay? Electrons flow, okay? In the conventional theory, they flow from positive to negative, okay? And that's how all automotive systems are set up. You have negative ground, right? So you have the positive flows through whatever component to a ground and back to the negative battery, okay? That's the conventional theory. Yes, exactly. Electrons flow in one direction from positive to negative, okay? All automotive schematics that you guys are going to be dealing with use conventional theory, okay? Positive to negative, right? Negative ground. Very easy to remember. Now, this is actually a really funny story here. What is electron theory? There is electron flow from negative to positive. This is actually what takes place, okay? Let me just see if I can't remember, even though I literally just kind of went through this. All right, so electron theory. I'm not going to talk a whole lot about electron theory, and this is why, because I don't want to confuse you guys, okay? I want to keep things simple. The key to electrical is keeping it simple, all right? Keeping it simple, the basics: power, ground, resistance, current flow, voltage, so on and so forth, okay? Now, back in the day, okay, I'm talking like 1800s, they started making cars and electrical stuff like that. Conventional theory is what they thought happened. They thought it went from positive to negative. Electrons flowed from the imbalance from positive to negative. Now, I believe in maybe 1930s, 1920s, something like that. They're like, yeah, that is not what happens. It actually flows from negative to positive. And the world was like, we just kind of based everything that we have on the other way, and we're not going to change it. They're like, oh, yeah, okay. So conventional theory is what kind of everyone goes by. Now, that's important when we talk about the left-hand rule and the right-hand rule and magnetism and all that type of stuff, but that is a story for another day, okay? All right. Take a break from all that stuff we just learned. This is important. What unit is used to measure current flow? Amps. Amperage is current flow. Okay. If we are using the official Ohm's law, we're going to get to Ohm's law. We're going to take a deep dive into Ohm's law. Okay. It uses I. Okay. I for intensity. Okay. Or, a big A is amps. Okay. Think water flow, gallons per minute. Okay. It's current flow. You use an ammeter to measure it. Okay. Now, just thinking about this, how do you measure the current of, how do you measure the water flowing through a hose? The amount, the current flow are going through the hose. Can you just take your hand and grab the hose and be like, yeah, I know how many gallons per minute? No, you need to have a meter in there measuring it. Okay. Yeah, 1 ampere, okay, amp is a movement of 1 coulomb, which is 6.28 billion electrons past a point in 1 second. That's 1 amp. We are not going to be doing that calculation, so don't you worry, okay? An ammeter, just like I was saying with the water flow meter, okay? It's installed in the path of electrons, and that's going to be important when we start using how we measure voltage, resistance, and current flow with our multimeters, okay? The unit of electrical pressure is voltage, okay? 12-volt battery, okay? This is the pressure, all right? It's the electrical potential, okay? In Ohm's law calculation, it's E for electromotive force, okay? So you would see that in an ASE. It would be EI and R for resistance. It is possible to have electrical pressure without any flow. All right. So think water. You have a pressurized container or something like that, right? With no flow. So you can have a battery, fully charged, 12.6 volts, full of potential, sitting on the bench. There's no flow, right? But it is charged. It's the pressure. Okay. It's got 12.6 volts ready to power up that car. Okay. Voltage is pressure. Okay. DC, we use direct current in automobiles. Okay. The only thing that really is alternating current is, some motors and the alternator, right? We're not going to worry about that right now. All right. Resistance. Ohms, or the little omega sign, okay? It is the opposition to flow. Remember, ohms is opposition, okay? Ohms is resistance, okay? The resistance of that material is going to depend on the material used as a conductor. Also, how long the wire is, that type of stuff, okay? The longer the wire, the more resistance it's going to have, okay? No, I'll tell you guys about that later. We're going to be talking about this in class and everything like that. So don't get too worked up if you can't figure it out or whatnot. All right. This guy right here, I found this picture. Actually, I don't know if I found it or someone sent it to me. This picture sums it up perfectly. Okay. You can see your little right here. Sorry. You got your volt, which is the pressure. It's pushing the amp, which is the actual flow, and you got your ohm, which is the resistance. Okay? So voltage is pushing current through the resistance. All right, this is exactly the relationship between these here. Okay? Yeah, I think that's a great picture because it really sums it up. And it's kind of funny, too. So, all right. Let's keep moving here. All right, so yeah, there you go. Resistance. Stop, right? Great picture. Resistors, we're actually going to measure resistors. All right. Not going to get too in it right now, but if you ever see this, if you ever looked at a circuit board, you see these things, they're resistors. Okay. They're providing resistance, maybe to protect electrical circuits. Maybe, you have, 12 volts or whatever, but you only want 5 volts. It's going to go through resistors to kind of slow it down. All right. All these bands on it actually mean something, but we're not going to get into that right now. They basically tell you exactly how many ohms are in the resistor. Okay. A potentiometer, okay, is a variable resistor. You have your reference voltage. This would be throttle position sensor, some sort of sensor, a position sensor, basically, accelerator pedal position sensor. Basically, this is like a manual, the closer it gets to the, it's okay. So actually here, where's my mouse? Where's my mouse? You guys see my mouse? I can't see my mouse. Anyways, we'll talk about these more in class, okay? But basically, a potentiometer is a variable resistor. A rheostat is a 2-wire variable resistor. We're going to get into all these much more. We're going to be testing with these, all that type of stuff, okay? All right, so to harp on the fact that electricity is the movement of electrons, okay? I got a couple of videos here for you guys to watch about the 6 sources of electricity, okay? What, especially in cars, and when we get to engine performance, we really learn about the, how sensors interact. We're going to talk about like how these are all used to generate electricity as sensors. Like a NOx sensor is a piezoelectric crystal inside there, okay? So first one, friction, static electricity. And I have this funny video here from Family Guy with Peter Griffin, and you guys, I'll just let them take it away. But I think everyone understands friction and everything, okay? But have a look. All right, so we're back. Great video, always a good one. Heat, thermoelectricity, okay? How does heat generate voltage, okay? If you have 2 different metals together and you heat them, they are going to generate voltage, okay? I actually have this really cool video here. The actual video is, and if you go to the YouTube video, if you guys actually want to watch this entire video, you guys can go to the YouTube of this lecture, and I have the link there for it, okay? But we're only going to watch a quick clip, just really this clip right here where he's heating it up just like he has, very similar to like what that picture is, okay? So have a look.
Today we will talk about thermoelectricity, which is a phenomenon that appears when we make a junction of 2 different metals. And it can appear in 2 different ways. One is the Seebeck effect, which is the direct conversion of heat into electricity, and the Peltier effect, which is the conversion of electricity into heat. Let's make a demonstration. This is a junction of 2 different metals that is connected to the multimeter. This is a copper wire, and this other one is wire from a paper clip that is covered with nickel. So it is a copper-nickel junction. I'm going to apply heat to the copper and check the voltage in the multimeter. It starts to rise as the copper heats. So we have 1 millivolt. And as the junction cools down, the voltage again starts to drop. I'm going to submerge it in water to cool it down. And you can see that we again have 0 voltage.
All right, so we're back. All right, next one, light, photoelectricity, okay? Ambient light sensors, like when it starts to get dark out and the lights turn out automatically, there's an example of how that's used in a car, okay? Now, the photoelectric effect, this is a great video. It's only like 3 minutes. It's a great video how he shows how UV lights, cause that movement of electrons. Because that's what it is. It's the movement of electrons. All right? Have a look.
One of the big ideas in physics is that light can behave as waves or particles, and this demonstration of the photoelectric effect is a really great way of introducing that idea. What I've got here is a zinc plate, and if you want the demonstration to work, it's absolutely essential to give it a good scrub on both sides with a bit of iron wool, and that just removes the surface oxide layer. I then place the plate on top of this gold leaf electroscope. I've also got an ordinary desk lamp and a UV lamp. Now, in order for the demonstration to work, this plate has to be negatively charged, and I can do that using the method of charging by induction. Now let me show you that again. I've got a perspex rod here, which I can make positively charged by rubbing with this bit of cloth. I bring the rod close to the plate, touch the plate with my finger, remove my finger, then remove the rod. Now watch what happens when I shine visible light onto the plate. Absolutely nothing. That's actually a really important part of the demonstration. Your students need to notice that with visible light, nothing happens. But watch what happens when I shine ultraviolet light. You can see that the gold leaf immediately starts to fall. And that must mean that the UV light is somehow discharging the electroscope. We know that we started with negative charge on the plate, so the UV light must somehow be releasing the electrons. And the important thing to notice is that it's the frequency of the light that makes a difference. Remember, with a visible light, it doesn't matter how bright it is or how long it shines for, it doesn't release any electrons. Now, this phenomenon cannot be explained using a wave model of light, but we can understand it if we adopt the idea that radiation arrives at the plate as packets of energy, which we can call quanta or photons. A single photon of UV light can release a single electron from the plate. However, a single photon of visible light has less energy and so cannot release an electron. Now, this is a relatively simple demonstration to do, but it took the genius of Albert Einstein to explain what was going on, and it was for that work that he was awarded the 1921 Nobel Prize, not his work on relativity.
All right, so we're back. Next one, pressure, okay? Electrical pressure. Piezoelectricity, okay? You see how there's a crystal in there? It's not just for hippies, okay? Crystals actually can generate electricity, certain crystals, okay? Electron flow is produced by pressures on certain crystals. Now, this video here, this guy takes apart. All right, so aim and flame. Okay, you take that trigger and it goes like click. It's kind of hard to push, and it goes click, and then starts the spark. That starts up the lighter. It's piezoelectricity, okay, or piezoelectricity, right? I can't say it, but I know what it is. But yeah, this is kind of a long video, but this is the best video out of any of these. The guy does a great job, so have a look.
When you press down on the trigger of a barbecue lighter, you'll notice it's quite hard work. Like, it's not like pressing the button on a remote control. You actually have to put some effort into it. Hold on. And there's a reason for that. When you press down on the trigger, you're working against quite a stiff spring, so that all that work you do is stored as potential energy in the compressed spring. And in front of that spring is a tiny hammer, so that when the mechanism finally gives way and the spring is released, all that potential energy stored in the spring is turned into kinetic energy in the hammer. The hammer then strikes a special kind of crystal called a piezoelectric crystal. And when you hit one of these things, it generates a voltage across the crystal. This is the inside of a barbecue lighter. This is the mechanism that houses the spring and the hammer and the crystal. These two wires are coming off the crystal and they're drawing that voltage up to the top of the lighter here. There's still a gap between the two wires at the top here, but the voltage that you produce when you press down on the piezoelectric crystal is so high that electricity can actually jump across that gap, producing a spark. If you send a flammable gas up to the top as well, then the spark will ignite the gas. For a while now, I've wanted to understand how the piezoelectric effect works on the molecular level, and I finally do. And I've also built something to make it easy for anyone to understand how it works. So that's what this video is about. There's a few different types of piezoelectric crystal that you can buy, but I'm going to look at quartz in particular, which is the first piezoelectric crystal to ever be discovered. This is what a giant quartz crystal looks like. It's also a healing crystal, according to the website that I bought it from. It will align your chakras. I don't know if you take it orally or... If you were to take a slice of quartz away from this crystal and compress it, you'd be able to measure a voltage across the slice, but you'd have to slice it at just the right angle like this. I don't know if this is the right angle, but it'd be something like that, and it's got to be just right. And to see why you've got to get the angle just right, we need to look at the lattice structure of quartz. So quartz is made of silicon dioxide, so silicon and oxygen, and this is what it looks like. At first it looks like quite a complicated structure, but as you rotate the crystal, you find these symmetries like this one. And here's another. But there's one particular angle that I'm interested in, which is this one. Notice this hexagonal shape here. It's actually a spiral going into the screen, but for simplicity, we're going to think of it as a ring. So these three crunchy peanut butter lids represent silicon atoms, and these three smooth peanut butter lids represent oxygen. So when you compress a crystal of quartz, you're squishing these hexagons. But crucially, the bond between oxygen and silicon isn't quite even. Like, the oxygen is a bit more aggressive in the way it holds onto its electrons. So the oxygens are a little bit negatively charged and the silicons are a little bit positively charged. So think about where the average of all the positive charge is in this diagram. It's a bit like the center of mass, but it's the center of charge. So it's there in the middle between these three silicon atoms. But watch what happens when you compress the crystal. The two side silicons move outwards, but they don't move vertically. And the bottom silicon moves upwards. So the average position of these three positive charges moves upwards slightly. And similarly, think about the average position of the three negative charges. Look, the two side negative charges move outwards, but that top negative charge moves downwards. So the average of the three negative charges moves downwards. So when you compress a crystal of quartz in this exact orientation, you're slightly shifting all the negative charges in one direction and all the positive charges in the other direction. Suppose you've got a square slice of quartz crystal. Let's represent all the positive charge as gold and all the negative charge as red. And in an uncompressed crystal, those negative charges and positive charges overlap exactly. And so you've got this neutral greenish color. But when you compress the crystal, the negative charges shift in one direction and the positive charges shift in the other direction. In the bulk of the crystal, it's still neutral overall. But at the faces, you've got this buildup of positive and negative charge. If you then wire up these faces, well, the positively charged face will be trying to pull electrons towards it from inside the wire, and the negatively charged face will be repelling electrons. And if you bring the ends of those wires close enough together, the electricity will be able to jump the gap, producing a spark. So that's how quartz is piezoelectric, but in general, any crystal can be piezoelectric so long as it fulfills a couple of criteria. The first one is that the lattice needs to contain some polar bonds. That just means that some of the atoms end up with a slight positive charge and some of the atoms end up with a slight negative charge, like silicon and oxygen in quartz. That's why diamond isn't piezoelectric. You can squeeze a diamond as much as you like, but all the carbon atoms inside are neutral, so there's no charge for you to move around. The second criteria is more subtle. It's to do with symmetry. The crystal needs to have a certain type of symmetry, or more accurately, a lack of a certain type of symmetry. Take a look again at this hexagonal arrangement of atoms from the quartz crystal. Look at this silicon atom and then draw a line through the central point to the opposite side and see what's there. It's not another silicon atom, it's an oxygen atom. So there's something different on the opposite side when you go through the central point. That means it doesn't have point symmetry. To see why a lack of point symmetry is important, look at this arrangement of atoms that does have point symmetry. See how silicon atoms are opposite silicon atoms, oxygen atoms are opposite oxygen atoms. When you compress the crystal, you move the charges symmetrically, so the average position of those charges doesn't change, it stays in the middle. The piezoelectric effect has a lot of uses besides just a high voltage power source like in a barbecue lighter. It can also be used as a sensor. This is a piezoelectric disc. It's probably not quartz, it'll be something else. And if I press down on the disc, I can get a bit of a voltage across it. It's sensitive enough to be used as a pickup for sound, so I can actually use it as a microphone.
It's not a great microphone, but it is a microphone.
Interestingly, the piezoelectric effect is reversible. Actually, in a previous video, I mentioned how speakers can be used as microphones and microphones can be used as speakers. And it's true of this piezoelectric microphone. It can be used as a speaker.
It's not a great speaker, but it is a speaker.
When you apply a voltage across a piezoelectric crystal, it will deform. It's the opposite of the piezoelectric effect. My absolute favorite example of the use of the piezoelectric effect is in the quartz watch. Inside one of these watches, there's a tiny crystal of quartz that vibrates exactly 32,768 times per second. If you know your powers of 2, then that might sound familiar. But why? Well, this video is already getting too long, so my next video is going to be about the amazing mechanism inside a quartz watch.
All right. So crystals, look at that. They might not heal you, but they can generate electricity. It's kind of cool. And then chemical. I'm not going to go too deep into, I'm not going to have you watch a video on chemical right now because we're going to be talking about batteries before long. So batteries, right? And then magnetism. Magnetism is the coolest stuff, like I was talking about with ignition. Well, I want you to just think about this. You have a motor, starter motor, and you have an alternator, okay? One of them uses electric current to generate magnetism, okay? So a motor does this. And magnetism, the other uses magnetism to create electric current, okay? Electromagnetism, right? Anytime you have a conductor, this is a wire, okay? This is a copper wire. It's a conductor, okay? The valence electrons are nice and loose. Doesn't take much to push them over the edge. If I take a magnet and I pass that over, the conductor, the magnetic field of that magnet causes the electrons to shake up and creates electric current. Okay? That's so magnetism is creating electric current. Now, a magnetic field, anytime you put current through a conductor, it creates a magnetic field. Okay? So now we're doing the opposite. I have a permanent magnet and I have a conductor. Okay? I got a wire. And this is a motor, right? I have a permanent magnet and I have a conductor here. I put voltage through this like a starter. Okay? You turn the key, goes through the windings, it generates a magnetic field. Now that magnetic field and this magnetic field, what happens when opposites attract? Or I'm sorry, what happens when like charges what happens when like poles, what am I trying to say? North Pole, they're going to push away from each other, right? Now you got that, and all of a sudden they start moving, right? Because like, nope, now you're north and I'm north now, and then they move. That's basically how a generator or a motor works, okay? So we're gonna do a whole unit on it, all right? So sorry if that was a terrible explanation, but That's all I got for right now. So I hope you enjoyed this. This is only the very beginning of your electrical journey. We're going to take a deep dive into this, okay? But I want you guys to remember as we start on this, don't get too overwhelmed, okay? Keep it simple, all right? If you don't understand it right away, don't worry about it. If you need to sit down with me as we go through this course and we need to talk about it to death, let's do it. All right. Don't be afraid of electrical. Okay. Everyone's like, oh, I don't deal with electrical stuff. Trust me, it's complicated, but it's not overly complicated. Keep it simple. Okay. So I'll be seeing you guys soon. Bye.